I'm very happy to introduce Professor Debajyoti Choudhury from Delhi University. He was a long time ago a student at IMSC, a year junior to me. He and his guide together migrated to PRL in Ahmedabad, and he completed his PhD from there. And subsequently, he was at many places before settling down at DU. Debu has worked in many areas of particle physics phenomenology and is famous for his not so wild ideas, two of which he is going to talk about today. Debu.
Thank you, Indu. Sure, thanks. Thank you, Indu, and it's fun to be back. Though I have been haunting this place in between. So I was here, 35 years ago, a little longer, and I see some of my teachers here, some of my fellow students. Okay, so today my talk today, since this is a mixed audience, I decided after some initial efforts that I'll not talk about what I normally work on, which is particle physics, partly because that tends to get too technical, and partly because I saw that at least two particle physicists would be speaking before me. So too much of a good thing is not good. So I'm staying away from particle physics. And I'm talking about a couple of rather crazy ideas that one had looked at. And one of those ideas had its genesis in IMSC. So I feel nice about talking it here. And I was not the initiator by any means. So I'll just mention it while I'm going about with my talk. So, evolution of the universe has everything to do with gravity and matter. And just to set our notation, since this is a mixed audience, but maybe I don't need to. So, gravity is, of course, a theory of geometry and energy momentum, where the variables that one uses are the metric, which for us means a measure of distance. And I've given here, I've got a pointer. Oops. Oh, which one? The top one. Okay. So what's the metric? Metric is something that gives you a notion of the distances. So for example, if I write things in the Cartesian coordinates, distance is given by dx squared plus dy squared plus dz squared, those being the infinitesimal variations. And so I would write ds squared as like this, and g mu nu is diagonal of in the 1, 1, 1. It's the same thing I write in polar coordinates. So my distance squared goes like this, and so now my metric is a different beast, which can be written like a diagonal matrix once again, 1 r squared and r squared sine squared theta. This everybody knows. And again, going back to a familiar thing, if I look at a divergence of vector, and I could have looked at curl or a gradient or whatever. So divergence of vector in Cartesian coordinates is given by this, whereas in polar coordinates is this. And the idea of writing this is to just remind ourselves that when we talk about, say, a divergence of a vector or a curl of a vector, etc., it's not just the mere derivatives of the components that come in, but there are, in addition, some functions of r theta and phi, which multiply just the original guys Vr, V theta, and V phi, without the Vr theta phi being taken derivatives. Okay, so these additional functions together give me what's called a connection. So in the simplest cases, the connections are given in terms of the derivatives of the metric, but in the most generic case, it doesn't have to be so, and this is what I'm going to use a little later on. Once again, to remind ourselves of something simple, a point particle motion. So supposing a point particle is moving and it has coordinates, say qi, okay, in 3 dimensions, say x, y, z. So one defines something called a Lagrangian, which is in general is a function of q, q dot, and not so common q double dots. And the equations of motion as derived from this Lagrangian would be given by this. Okay, so, and that gives me the equation, say for example, Newton's laws would be obtained if I assume a certain Lagrangian. And this is something that everybody is familiar with. When we come to gravity, which is nothing but dynamics of the geometry, my coordinates are metric and maybe connection. And my Lagrangian is a function of the metric or the connection and their derivatives. And this together gives me Einstein's theory of gravitation, which tells me that geometry and matter are interlinked. Geometry affects the motion of matter, and the matter distribution affects geometry in turn. And this will become clearer when we look at certain solutions of Einstein's equation. For example, soon after, within a year of Einstein's writing down his equations in 1915, Schwarzschild found this solution where I've got an empty space except for a mass, m, and the space-time distance, the invariant distance, is given by this function. Okay? So this immediately tells me, okay, so even if we neglect this dt square part a bit, if I just look at this, it tells me that there is this extra factor, and this tells that in the presence of matter, the shortest path looks curved. Okay? And this will, consider m to be the mass of the sun. This will also give immediately the motion of the earth around the sun, just starting with this definition as the straight line. Okay? So soon after that, in 1917, de Sitter found another solution of Einstein's equation where one had an empty universe with something called a cosmological constant, and that led to an exponentially expanding universe. Okay? It was curiosity at that time. Okay? We'll come back to this in a little while. In another 5 years, Friedman found a third solution. Okay, there were many others. There was Reisner, Nordstrom, there was Kerr, etc. Friedman found another solution which pertained to an isotropic and homogeneous universe with arbitrary types of energy. This arbitrary types of energy includes energy due to matter, energy due to radiation, etc. Okay? So I'm not giving out these solutions. The Friedman solution I'll talk about later. But this isotropic and homogeneous universe, that is supposed to mirror the known universe at large distance scales. Okay? Of the order of, say, 20 megaparsecs. Okay? So if I sort of average out the universe at that scale, I will get an isotropic and homogeneous universe, and the Friedman equation is supposed to model that. Going back to observations, 1910s, Westo-Slipher saw that extragalactic objects seem to be moving away from us. 20s, Hubble looked at Slipher's data more carefully, made more of his observations, and found a remarkable result that objects farther away are moving away faster. So the velocity with respect to us seems to be directly proportional to the distance with respect to us, and the distance, okay? Today, we know that the relationship is not exactly linear, but that also we'll talk about later, what that relationship is. Now, if objects farther away are moving away faster, it means what? That the universe is expanding. If the universe is expanding today, I run the clock backward, then the universe must have expanded from a tiny blob, which some people call the primeval atom. Okay? And that led to a Big Bang, the idea of a Big Bang. That, far back, the universe was in a small place where it expanded. Now, if I compress everything, say I think of the universe as a gas, I compress it, of course it will become very hot. And so in the early universe, the early universe was extremely hot, and there was an era where the ambient energy was so large that even all the hydrogen atoms, and by corollary all the atoms, were ionized. Okay? And much before that, there was an era where there was no nuclei even, because the nuclei broke. Okay? Now, this formation of nuclei, I can start from the Big Bang, work through my equations, and I get something called the Big Bang nucleosynthesis, and it reproduces the observed nuclear abundances in the universe very well. So this is considered a major success of this paradigm. So I said there was a time when the protons and electrons could not form atoms. Okay, as the universe was expanding, it cooled down, they got bound, they formed hydrogen, and we know that the hydrogen binding energy is about 13.6 electron volts, so that energy got released in photons, okay, which gave the cosmic microwave background radiation, which is a black body radiation with an excellent fit to the radiation curve. I mean, the best known black body radiation is the CMBR. So 13.6 electron volt, you can convert into kelvins, okay. So today, and it's a pretty large number, okay. It's more like 3000 kelvins. Today, the universe has cooled down to about 2.7 Kelvin, and that is the temperature that Penzias and Wilson measured to get the black body radiation. Now, coming back to the last 30 odd years. In 1992, the Kobe mission flew, and it looked at the black body. Of course, it reconfirmed the black body spectrum, but found that there were hot and cold patches in the sky, and the degree of hotness or coldness, the relative temperature, delta T by T, was of the order of 10 to the power minus 5. Okay. And now, for the young members of the audience, you should try to find out how they could have measured 10 to the power minus 5 in black body spectrum. Subsequently, WMAP resolved this Kobe to this, and Planck, still 10 years later, got this, this kind of details in the spectrum. Okay. So the study of these small fluctuations, correlations between fluctuations, temperature correlations, and then there's polarization, etc. Okay, they lead to a measurement of various cosmological parameters. What kind of measurement? So let us look at this. So everybody here presumably has heard of something called dark energy. So if I look at the energy budget of the universe in terms of matter, by matter I include dark matter and the dark energy. Now, I look at galactic clusters. They gave me this kind of a correlation between matter and dark energy content of the universe. Okay. Study of supernovae gives me this. Study of CMB gives me this. And so combined, I have only this small red circle. So very, very precise. Okay. This, somebody, Rohini, I think, talked about error bars being in the exponents when we were young. Today it's no longer true. And this is what we have for the energy budget today. So today we know that about 23% is dark matter, 4.6% atoms, and 72%. Have I fallen silent? No. 72% in dark energy. This was not always so. If I look close to the time when the recombination era, the proton, electron, when proton and electron recombine to give you hydrogen atom, the ratio was quite different. And this ratio was different because various components, their energy density content evolved differently. Some of them, like if it's an ultra-relativistic object, the energy density falls like 1 by scale, the size of the universe to the power 4, whereas for non-relativistic matter, it will fall as 1 by radiation to the by size to the power 3. So the various things, and the dark energy does not fall at all with the size of the universe. So here, there was no dark energy. Here, dark energy dominates today. Okay. A lot of people also talk about this as the coincidence problem, which I don't think that's such a problem. How much time have we taken already? Okay. So now I'll just talk about some problems. Now, this plain Big Bang theory had many problems, and to cure some of these problems, okay, the problems called horizon problem, flatness problem, magnetic monopole problem, density perturbation problem, etc. And to cure many of them, one invoked a period of accelerated expansion, which is called inflation. Okay, it supposedly solves all these problems, and so okay. However, although I had said before that the cosmological constant can lead to accelerated inflation, the cosmological constant is not enough to do this, because an accelerated expansion powered by the cosmological constant cannot be stopped. So if the cosmological constant had done that, the universe would have been accelerating madly ever since, which it did not. The accelerated expansion was only for a short time span, and then it stopped. Okay. So the traditional way is to invoke a scalar field, and then, even then, getting out of the scalar field driven inflation is not always so easy, and it needs some fine tuning. And secondly, the kind of potentials that do the job for you, at least do the job as far as cosmologists are concerned, those kind of potentials are typically hated by particle physicists for a multitude of reasons. So there is a bit of a tension. Secondly, what of pre-Big Bang? Okay. So if the universe has been expanding forever, there must have been a time when the universe was infinitesimally small, and we have no idea how to deal with that. Most of the treatment of cosmology is always classical, at best semi-classical, and for infinitely dense universe, we cannot use those, and all bets are off. So this, as we reach the singularity, we have no idea how to deal with things. So these two problems I would request you to remember, because this is something that I'll be addressing. Now, one more problem, observational problem. It's been much in news in the last few years. It is so-called Hubble tension. So what was the Hubble tension? So I told you about this Friedmann solution, and so Friedmann, Lemaitre, Robertson, Walker, etc., etc. It says that the metric for the universe on a large scale is given by this. Okay, there's a single function, okay, which multiplies this, and I am also assuming flat. If it's not flat, I can introduce some other factor which I don't want to at this stage. Okay, so if I have that, okay, and this factor, the sole factor, is called a scale factor because it sets the size of the universe. And once we start with this, we see that the Hubble expansion rate is not constant. Rather, it's given by this ratio, the time derivative of A divided by A. So the logarithmic, ddt of log A. Okay. And by convention, the value of the Hubble constant today is denoted as H0. Okay. Now, Einstein's equation, as I said, relate geometry and energy momentum of the matter or radiation, etc. So given the radiation, matter, and maybe the dark energy, and when I say matter, I include visible and dark. So given all of this, h of t is defined. Okay. So given h of t, I can work, okay, whatever the values back then, I can work through today, and I can determine what h naught is. Okay. Starting from what Planck has seen, okay, I can get it. And once I do that, I get this value, 67.8 plus minus 0.77 kilometer per second per megaparsec. Okay. On the other hand, if I look at relatively nearby objects, supernova 1As, Cepheid variables, tip of the red giant branch, data from Hubble Space Telescope, etc., etc., I get this value. And between these two values, there's a more than 4 sigma discrepancy. Okay. Now, is 4 sigma discrepancy something to be worried about? Well, I leave that to you to judge. 4 sigma discrepancies have long been known to go away, but supposing it stays, then a reconciliation of these two objects would need changing evolution history, because this is something that we directly measure, this is something we infer, and here the history of the universe has gone in, and that would need to change. Okay. So here my first this thing starts, the wild ideas start. So non-invertible metric. So we talked about this subject called the metric, the distance measure. Okay. So what if the metric is non-invertible? Okay. For example, in a Cartesian metric, supposing the Cartesian metric were like this, which means ds squared does not get any contribution from the x direction, it gets contribution only from the y direction and z direction. Okay. X separation has no bearing on distance. Okay. So that is okay. Now if this is so, then doing my usual formulation of gravity becomes a little tricky, because those of you who remember, to derive the gravity, to write down the gravity Lagrangian in the usual formulation, so-called Einstein-Hilbert formulation, I need to consider not only the metric and its derivative, but also the inverse, the inverse of the metric, okay, to get a scalar object. So that is why there's a problem. Apart from that, there is something called a Palatini formulation, where both metric and connections are used as independent variables, hence my original this thing of the connection. Now, for invertible metric, both of these guys are equivalent, both formulations are equivalent, and it can be shown rigorously. For non-invertible metric, they are not, and Ramesh Kaul and Sandeepan Sengupta here did a lot of work on this, and they are the ones who introduced me to this idea, and so my hat tip to them. Okay, and they found several very interesting features in this. Okay, I'm not going to be talking about what Ramesh and Sandeepan did, because they must have given talks here. So, but on the other hand, metric, okay, you would say that a non-invertible metric seems ridiculous, because we know from our experience that metric is invertible. Okay, it's 1, 1, 1, the distance, at least in Cartesian coordinates. So we have a different take. Okay, just, this is a speculative bit. Supposing the world is in 5 dimensions, okay, just for the heck of it, and we are confined to 4 dimensions, okay, and the 5D metric is assumed to be rank 4, okay. So 4 eigenvalues which are non-zero, and 1 eigenvalue which is 0, okay. I go ahead with this, And with the simplest construction, I can get the so-called late time acceleration that we see today, and for which one has to invoke a very tiny cosmological constant which people do not like. Okay, but let's be more ambitious. Okay, since the metric is non-invertible, we use the Palatini formulation. Technically, you should use the field binds, etc. Let's not go into that. But I write this Lagrangian, which is a 5-dimensional object, plus I can write a 4-dimensional contribution to the Lagrangian, which is confined to only this 4-dimensional hypersurface that we know of. Okay, I won't go into the maths, but it gives me such an expression. This Hubble constant or Hubble expansion rate divided by h naught square, which is today's value, I get in terms of these objects. Okay, it's a complicated looking expression. So where this omega m naught and omega gamma naught are matter and radiation energy decay. Okay, and these two are couple of parameters that appear in the theory. Okay, now once I get this, I can test it against supernova data and demand consistency with CMBR. Assume that I play this game. What do I get? Okay, so we did a Markov chain Monte Carlo, and there we get these values. Okay, so this is where I assume there's no radiation, and here assume a small amount of radiation that is consistent with what we know of the world today. And well, it's not surprising that nothing really depends on this. Okay, these two values are virtually the same. Okay, now note one thing, that this value of h naught is 72 plus minus this, which is absolutely consistent with the near field measurement. Okay, so one seems able to reproduce the near field measurement and or cure the. So this is a 2-dimensional this thing of the same thing, but since I'm running out of time, one can cure Hubble tension. It requires slightly less dark matter. That's not than the conventional idea. So that's not a problem. Dark energy is roughly same, but more importantly, okay, look at this parameter B, okay, which is a combination of these other parameters. Now the B value, you see its center value is 0.036, and on the negative side, the error is larger than the center value, so which means B can be negative within 1 sigma. Now what if B is negative? B is negative means the argument of the square root turns negative, which I cannot have. Okay? When will the argument of the square root turn negative? When this guy becomes bigger in magnitude than the rest. And when will that happen? When A becomes small. Okay? So which means that A cannot become very, very small. Okay? If I take this idea seriously, then if I have a slightly negative value for A, it can give me a minimal size of the universe. So the singularity problem would be avoided. Similarly, a maximal size of the universe also comes into being. Okay? It's a toy model. Okay? So should I believe in it? I'm not saying that one should, but it's curious. Now I have only 5 minutes. Okay, so wild idea 2. Okay, so wild idea 2. If I have delayed interactions, so now delayed interactions appear in many biological systems. Gautam here is an expert, and so are many others. Okay, so what if I try to apply this idea to cosmology, to gravity? Where do I get delayed interactions? It can presumably come from non-local interactions which could have their origin in string theory or loop quantum gravity or spin form. Anything one doesn't know, one ascribes to string theory. Okay. So we said that there's at large scales, we have this so-called Friedmann equation, which is this. The Hubble expansion squared is 1/3 rho t, where rho is the total energy density. Adiabatic expansion of the universe, along with first law of thermodynamics, gives me this, where P is the total pressure density. Together I get this, which I can rewrite like this. Okay? And this tells me that for an accelerated expansion to occur, I need rho plus 3p to be less than 0. Okay? That is not possible with any form of known matter or radiation. Okay? So usually one gets that by invoking this inflation, where I have a scalar field that rolls on a sufficiently flat potential, etc. So that's an ad hoc way of doing this thing, because this guy does not play a role in anything else that we can directly measure. Suppose we say, it's a very phenomenological answer, no theoretical mooring. Supposing we say that this A dot by A squared is proportional to rho at a past time. Not today, rho, but at a past time. Now, terrestrial experiments, the best experiments that we have done, says that this delay has to be less than 10 to the power minus 27 seconds or all. Okay. There is a long way to go before we reach the Planck length, where gravity becomes strong. 16 orders of magnitude. So if we have a small tau, small delay, I should not expect any effect in late time development. So I start with this, and I still do this adiabatic and first law of thermodynamics. I get my equation to be this, which has to be contrasted with the standard equation. Okay? No big deal there. First year, okay? Now, what about the matter? I take the simplistic attitude that all cosmologists take. I say matter is simple, and it's of the form where P, the pressure, is some constant times rho density, and then first law of thermodynamics tells me that rho goes like this. And where these three are various forms of W for various kinds of objects. Fine. So now, I am talking about the equation with delay, so I cannot use just one initial condition. I have to give initial condition over the entire delay period. So I do that. Okay? Now this is arbitrary. Okay? I assume that A at this epoch went as some function which is t to the power alpha. Okay? Now this function is not derivable within the bottle. Okay? I could have chosen, can I take 2 minutes extra? Just 2. Okay? I could have chosen other forms. Now if alpha is less than 1, the universe is decelerating initially with alpha less than 0 implying a collapse. Once I do this, once I solve this, in the first epoch, I get this, okay? And lo and behold, I get inflation, okay? Scale h of t, which is constant, so A going exponentially is the inflation, okay? So what do I find? I find a phase of fast growth exists for a wide range of A, and throughout inflation, rho plus 3p is greater than 0 in contrast to all known inflation models. Okay? Okay? The condition of inflation actually now reduces to this. Okay? The rate of growth is determined by initial matter density rho naught. Now, normally, energy density pulls you back. Here, we have the opposite thing, that instead of slowing down the expansion, the larger energy density throws you out with more violence. Okay? So, duration of the inflationary growth phase is only about this, and the universe quickly goes to a non-exponential expansion rate, okay, after this period. So the graceful exit comes out automatically. How much inflation? Well, that depends on what kind of parameters I choose. Okay. So this upper set, okay, in the tau rho alpha plane, the upper set is about 70 e-folds, and we need only 65 e-folds. The lower one is about 700 e-folds. Okay, 10 times larger. Okay. Dependence on W is small, as we saw seen. Okay. So as I said, the faster the universe was collapsing, the faster it rebounds back. To get an acceptable amount of inflation, I need tau to be order of 10 to the 2 to 10 to the 3 T Planck, which is reminiscent of the usual inflaton scale, being about 3 times 10 to the power 3 times below the Planck. Okay. So since Indu is threatening me, let me stop here.
And I'm very happy to do that.